Hello, this is a continuation of the single value decomposition work that we did earlier, and I wanted to use a program to find this for us. And the program we're going to use is called Octave. And if you type Octave space online, it'll search it out, and the first one should be octave-online.net, and that's going to be the program that we're going to use. So if we remember what we did last time, we found the SVD for this matrix A. We found the transpose. We found A transpose times A and A times A transpose. We found A transpose A's eigenvalues, which was 9 and 4. And then we found its eigenvectors and we normalized them. So now we have our matrix V. Since our eigenvalues are 9 and 4, our singular values are the square roots of that. And when we set up that matrix, we're going to put the largest value first, 3, and then the square root of 4 is 2. And by the way, the eigenvector that corresponds to the larger eigenvalue goes first, and then it goes in decreasing order. From there, we found that the eigenvalues for A times A transpose is the same, except if you have a 3x3 matrix, you're going to get one extra eigenvalue from our previous 2x2 matrix. And so the extra eigenvalues that you would get would be 0. And so we found the eigenvectors corresponding to these things in order again, starting with 9, and then with 4, and then with 0, and then we found the columns for the matrix U. Okay, so this is how we found our values, or our decomposition. So our decomposition would be U times the sigma times V transpose, and then that should get us back to A. So what I wanted to do is, this is the brief sketch of the kind of like the algorithm to find that, and I wanted to go into Octave, which is a free version of MATLAB. Okay, so here we're going to define our matrix A, and to get a matrix, we're going to write them with a square bracket. So I'm going to let A equal to the square bracket of 1, 2, semicolon for the new row, 2, 0, semicolon, 0, 2. And so when you press enter, you'll see that you have your matrix all set up. The transpose is quite easy. It's just whatever the matrix is with an apostrophe. So A apostrophe or single quote, whatever, will give you the transpose. All right, and the first thing we wanted to get was A transpose A. I'm going to call this matrix B since I will refer to it later. You don't have to, but it's just a little bit more convenient. So A transpose, remember, was the apostrophe multiplied by A, and then when you press enter, you're going to get a square matrix that is symmetric. So we expected that. Then we're going to find the eigenvalues and eigenvectors of this. So there is a command called eig, and so we're going to run eig-b. But eig-b, if you run it just as is, it's not going to give you everything. It's going to give you the eigenvalues, but it doesn't give you the eigenvectors. So if you want the eigenvectors as well, you're going to want to store it in a couple of matrices. So their response or their answers will be in a couple of matrices. So the first matrix will be the matrix of the eigenvectors. So let's call that Bx for the eigenvectors, and then I'll put a comma, and then I'll call BL to be the eigenvalues. Okay, so each of these will output a matrix that has that information, and you'll see the eigenvalues, how it's going to be set up in a matrix. So we'll set eig-b equal to this Bx and BL set of matrices, and when I press enter, you'll see the Bx would be this negative 0.8 and 0.4, 0.4 and positive 0.89. Now, the columns here are the eigenvectors corresponding to the eigenvalues. We saw that the eigenvalues were 4 and 9, but you'll see here that clearly it's matching with the eigenvalues that's given up on top. Now, since there are many answers for your eigenvectors, they do normalize it, so that's great for us because now it's already normalized. Now, the thing about our V is that we want our V so that the eigenvector for the largest eigenvalue goes first. So I just want to switch the order of this. And to do that, without actually having to type it in, I'm going to define my new matrix V now. It's going to be in square brackets. And I'm going to keep the first column. So the first column comes from Bx. And this is just some syntax notation that is part of MATLAB. I'm going to get that matrix Bx. And I'm going to, that first one, the colon here, refers to the first row, or all the rows. And then I'm just going to want the second column to be first. So this here, the Bx parentheses colon comma 2, gives us the second column of the matrix Bx. And now I'm going to put that in the first column. And then I'm going to put a comma, and then I'll have Bx. Now I'm going to access the first column. So essentially, I switch the first and second column. So if I type enter here, and I compare my V output with the Bx output, I see that my columns were switched. Okay, so that is my matrix V. Now the sigma, I can just make that up, and I'm going to call it S instead of calling it sigma. And remember that our matrix, our original matrix A was a 3 by 2, so I'm going to want a 3 by 2 here. I'm going to take the largest eigenvalue, which is 9. I'll take the square root of that, so that's just 3, or I could do square root of 9. And then comma 0, colon next line 0, comma the square root of 4. Again, that's just 2. I didn't need to do the square root business. And then 0 and 0. And then close that. Okay, so you'll get some pop-up ads. Just close that out. And then press enter to get my S. So my sigma is going to be this matrix, which we saw earlier. Now to find U, remember U is going to be the A times A transpose. So I'm going to refer to it as C, just another letter. A times A transpose, and remember this was a 3 by 3 matrix, square matrix that's symmetric, and here is that square matrix symmetric. All right. Now I'm going to find the eigenvalues and eigenvectors of that. So eig C, and then inside of the square brackets I will type in Cx, comma Cl. So Cx will be my matrix made up of the columns that are the eigenvectors, and then the Cl would be the eigenvalues in the diagonal. So if I press enter, you'll see something weird happen now. I'm expecting my diagonal matrix to have a 4 and a 9, and you see this is 4.0 times e to the 0, so that's just in scientific form, and that's equal to 4, and this is equal to 9. Now this one is negative 3.3 times 10 to the negative 16th power. So 10 to the negative 16th power is a really small value. So this here is essentially 0. Now it's not exactly 0 in the computer because of some of the rounding errors that it's going to get. So when you see something written in scientific notation and then you see at the end E negative number that is more than 10, then you could probably assume that that's equal to 0. So if I scan the eigenvectors, I see this one with a e negative 17. So this is essentially 0 right here. This slot is 0. Okay, so keep that in mind. Now I want my U matrix, and my U matrix will switch the order of these things. So U is going to be equal to, in the matrix form, I want the CX, and I want the rows to follow along, and I want the third column first. And then I'm just going to copy this and paste it, or you can retype it, and then switch the order of these things so that the third column for the CX becomes the first column for U, the second column stays, and then the third column for CX is actually the first column, or the third column for U is actually the first column from CX. All right, so if we run enter and then we compare these three matrices, you can see the second column stays the same. The third column here with a 6.6, negative 3.3, negative 6.6 is actually the first column here. So that got swapped already. All right, so that's it. Just to verify, A is supposed to be equal to U times the sigma times the V transpose. So if I run that, I see, well, it doesn't exactly look like it, but let's parse through it. This is 1 times 10 to the 0 power, so that's just 1. This is 2 times 10 to the 0 power. This is 2. Now here's another one of those where I have a negative 1.3 times 10 to the negative 16th power. That produces a really small number, so that's essentially 0. This is also essentially 0, and then this is the last number here, 2. Okay? All right, so that's great. As an algorithm, though, you would expect something like a processing program, numerical program like Octave, to have a straight-up SVD command. And in fact, it does. So let's use that SVD command. So SVD is the command for A. So I'm going to run this right now, and I'm going to see I have the singular values for A, which is the square root of 9 and square root of 4. And notice that there's no 0 here because the singular values are just the non-zero, the positive eigenvalues, or the square root of the positive eigenvalues. But if I want the other matrices as well, I will need to actually include that in my output. So I'll start with a square brackets. And the first one is going to be U, and I'm going to call it U1 since I already called U something else. And then my sigma, I'm going to call it S1, and then my V, and I'm going to call it V1. And then set that equal to the SVD command for A. And if I run that, I see these values, and if it looks familiar, I don't know if you remember, but it should kind of look familiar. We see that your values, the first column of U1, for example, should match the first column of U that we have here. It looks like the last column is off by a negative sign. Actually, the next two columns are off by negative signs. They're still orthonormal. They're just pointing in different directions. So I think it would still be okay. And then I think we have that issue with a negative sign for V as well. But just to make sure this actually works, if you take U1, multiply it with S1, and then multiply it with V1 transpose, we should get the original matrix. Again, it's 1, 2, 2, and this is really small, so that's 0, 0, 2. All right, so that is a way to check your work. Okay, hope that helps.